chunky, but we're going to talk through them. So one of these is to do a heating curve, and the other is to do a titration. So I'm going to do the heating curve first, and then the titration second. So first of all, what is a heating curve? So this thing is a heating curve. So what is happening in this heating curve? Is you started off at the lower left with a solid, and what happens is the y-axis is temperature, and the bottom is time. The idea is that you're continually applying heat to a solid. And this could be for anything. We have a tendency to use water because it's something everyone's familiar with. But I mean, if you want to talk about what it takes to melt this like toy that I have, this little stress ball toy, we could do that. Because it's a solid right now, and at some point, we could heat it up until it melts. That's a thing. Um, so, but again, in general, you're going to see us use ice for the most part. Um, use water because that's going to be easier for us to deal with. So any of the um these are not vertical because they're at an angle. But essentially I'm going to highlight them. These lines here are all about heating something. So all of these lines here that I've just highlighted are all about heating something. So we have equations for that. This Q equals Sm delta T. Now, there is going to be a different specific heat involved and a different temperature range for everything, because if you're going to talk about heating liquid water, water is liquid at 1 atmosphere only between 0 degrees Celsius and 100 degrees Celsius. Outside of those ranges, you don't have a liquid anymore, and the specific heat is going to be different. So those are some of the things you have to keep in mind. These horizontal lines here and here are different. What these are is these are where you are going through a phase change. But we also have ways of dealing with a phase change. So if we're talking about solid to liquid, that's going to be our solid water to our liquid water. And this is just a chemical reaction that's going to have a value of delta H. So we can still get that information, but we're going to need a different mathematical way to do that. So what's going to wind up happening is when you have phase changes, you have one way of doing the calculation. When you're just heating a substance, you have a different way of doing the calculation. So what I'm going to take a look at, this is the example that I did in class. We're just going to change this a little bit. Let's go ahead and start at, just to be different, we're going to start, so with that amount, but we're going to start with water at 70 degrees Celsius and go to steam at 200 degrees Celsius. There's a different problem now. So one of the things we do have to recognize that's not here, but you need to know it, is that if we had to deal with freezing, going from ice to liquid water happens at 0 degrees Celsius. Here, we're going from liquid water to steam, and that's happening at 100 degrees Celsius. You have to supply that information. So you do need to have memorized the melting point and freezing point of water. Looking at this, we have a lot of numbers. We are going to be dealing with heating water, liquid, and we're going to be dealing with heating steam, but we don't have ice, so I don't need one of those specific heats. Likewise, I am going to be dealing with boiling, but I don't have to deal with melting. So the problem gave us a lot of numbers, but we don't actually need all of them. So we're going to go ahead and start with heating the water. If we were looking at our heating curve, we're basically starting like kind of here or so, where we have liquid water, but we need to heat it. So if we're starting at 70 degrees Celsius, we're going to heat it to 100 degrees Celsius. So we have to cover basically this chunk of the graph. So to do that, since we're heating a liquid is Q equals Sm delta T. So Q equals SM delta T. My Q is what I'm solving for. This is liquid water, so this is 4.184 joules per gram per degree Celsius. The mass is zero 0.5 kilograms, so I can take my 0.5 kilograms and say, hey, in 1 kilogram there are 1,000 grams, which then means I have 500 grams. So then to this, I have 500 grams. And then my change in temperature. This is again the part where I have to keep in mind what's going on, because even though the problem goes all the way to 200, I only have liquid water to 100. So when I'm looking at my final versus my initial, I need to keep track of the substance I have, and I need to keep track of what the actual boiling point is, because I only have water to 100 degrees Celsius. I don't have a liquid after that. So you do need to keep in mind what we actually have and what substance you're working with. So then I get a value for Q of 62,760 joules. Because we're going to be dealing with both joules and kilojoules, it doesn't really matter which one you keep, but we'll just leave this in joules for now. So next up, we're going to take a look at my graph. Now I'm in this in-between thing, but this is boiling. So the boiling thing is what needs to happen next. For boiling, I'm going from liquid water to gaseous water, and that's going to come with a delta H of vaporization. We're going to take a look. That was given in the problem. So the problem gave me a delta H of vaporization. This is in kilojoules, also per mole. So what I do need to do is take my 500 grams and say that there are 18.016. I have that memorized. You don't need to memorize it. You can go to the periodic table and figure out your molar mass, or the molar mass might be given in the problem. Also an option. But I have to admit that that is something that I'm just prepared with. 27.75 moles. And all we're going to do for this is my moles of water, and the delta H of vaporization basically says for every mole of water, because again, my equation looks like this, for every mole of water, that number, that 40.7, is the amount of heat required to go ahead and boil that, because you're disrupting all those intermolecular forces. So all I have to do is take my 27.75 and multiply it times my 40.7 kilojoules per mole. Now I do have the whole number still in my calculator, so my number is probably going to be a little bit different from yours, because I kept all those decimal places in my calculator. 29.6 kilojoules. I am again going to keep track of the fact that that's in kilojoules, because the other one was in joules. This is in kilojoules. Okay, we have heated the water. We have boiled the water. Now we have to heat the steam, because everything we just did at boiling was all at 100 degrees Celsius. We didn't get to move forward past 100 degrees Celsius until all the water boiled. I don't know if any of y'all have ever made candy before, but when you make candy, you can actually see this heating curve in action, because the temperature, you usually boil sugar water, a sugar water solution on the stovetop, and that thing will change temperature rapidly until it suddenly just seems to stop. And then you're like, "Wah, but I wanted my stuff to happen. Why isn't anything happening?" And it's because the water is boiling off. And then once all the water boils off, it starts to go again. So now we need to boil stuff. I left off at 100 degrees Celsius, so I'm back to Q equals SM delta T. But now I have steam, so now I need a different specific heat, 1.8. That is joules per gram per degree Celsius. The mass is still 500. That did not change. My temperature change now, my final is whatever's in the problem, 200 degrees Celsius right here. And the initial is wherever I left off. So 200 degrees Celsius minus 100 degrees Celsius. So yes, I did pick some pretty round numbers to make my life a little easier. 1.8 times 500 times 100 as the change in temperature gives me 90,000 joules. For a final answer, I do have to add all of these together. So for a final answer, I'm going to go ahead and work in kilojoules because that's just a little bit smaller. So this divided by 1,000 is 62.76 kilojoules. So I'm going to take 62.76 plus 1,129.6 plus whatever my final number is, 90. And after I add all of those together, so I'm just going to say add together, and then we get 1,282. Technically 0.36. Well, 0.4 is fine. Kilojoules. So do notice that most of that actually comes from the boiling, because boiling does require a lot of energy. So that is where the majority of that came from. But that's a heating and cooling curve. The main game with this is to, again, remember which equations you need. So it should kind of seem kind of familiar, like it's the calorimetry stuff. And to make sure that you're putting in the correct temperatures, because you're going to have some of those off the top of your head to know where you're actually starting and stopping, because it's not just the whole thing in one go. So that is a heating and cooling curve. The last thing was to do a titration. Take a deep breath. So these were questions that were asked by my class in advance. And honestly, they're good questions because they are long. So what's the molarity of an unknown acid if a 25 milliliter sample is completely neutralized with 3.5 milliliters of a 1 molar strontium hydroxide solution? So this is a titration question. It says completely neutralized. And it says acid. Oh, this should have said monoprotic, just so that you would know that there's only one proton to deal with. And then you have a base. This is actually a strong base. So this is a titration problem. Acids, bases, complete neutralization. So since it is an acid-base problem and they're completely neutralized means the moles of H plus have to be equal to the moles of hydroxide. I am going to use this. I know so this is also the thing where if your instructor has a different way of doing the problem, what I would recommend that you do is pause the video here, try it out on your own, looking back at your notes for the way your instructor did it, and then just skim forward to see my answer. Because there's about 3 different ways to do this problem, and they all work. But I'm only going to do it one way, maybe 2, depending on time. I forgot I have a meeting at 9 o'clock this morning. Whoops. That's just me. So we're going to deal with this whole notion of moles. So while I don't have information about all of the moles of the acid, that's what I want, I do have enough information to get moles of my strontium hydroxide. So that's the first thing that I'm going to do. So I'm going to treat molarity like an equation, that molarity is just moles per liter. And so I know that this is 1 mole, or this is 1 molar, and a certain number of moles. And then I need that, so this is from the problem. So there's my 1 molar right there. My 3.5 though is in milliliters. I actually have liters, so I do need to go ahead and say that there are 1,000 milliliters in 1 liter. So this then is 0.0035, right? Yes. So that also then means, because I chose 1 molar, I multiply this to solve for the number of moles, and that is also my number of moles. Maybe I should have not made this a 1 molar solution to make the math a little bit more interesting, but c'est la vie. But this is the moles of strontium hydroxide. That's what those are. So this is the molarity, but this is the molarity of strontium hydroxide. It's not the same as the moles of hydroxide here. And I know that because I have this number 2 right here as part of the formula. As part of the formula, it tells me, hey, this thing comes with 2 hydroxides. Since it comes with 2 hydroxides, for every 1 strontium hydroxide, I actually have 2 hydroxides. You can get that a couple of different ways. So like I just highlighted, that little 2 is a subscript. You could do it that way. You can also go ahead and think, what would this look like as a strong electrolyte? So you can also go ahead and do some math on here, considering what would happen to this if it was a strong electrolyte, and how would I write this out if it was an ionic equation? And that will also get you that relationship between the strontium hydroxide and the hydroxide. So now I know I need to multiply that by 2, so that gets me 0.007 moles. And this is now moles of hydroxide. Now, because this is a titration, I started off by saying, hey, this is a titration. It's completely neutralized. That means the moles of H plus are equal to the moles of hydroxide. So now I'm going to use this in my titration and say, for every 1 mole of hydroxide, I actually have 1 mole of H plus. So this is also moles of H plus. But I really want acid. This is that part where I said, when I did the problem, this really should have been a monoprotic acid, because that's the moles of H plus, which actually does also mean, since it's a monoprotic acid, that should have been part of the problem. This is also the moles of the acid itself, the moles of the unknown acid. So that is moles of the acid itself. I do have a volume for this in milliliters. I'm not going to scroll back right now. It's 25 because I was picking a lot of really round numbers. So I'm going to take my number of moles and divide it by 25 milliliters. Which gets me a final molarity of 0.28. Looks like that. Something to keep in mind. This is a problem that has a dibasic base. So because it has a dibasic base, that's why we had to deal with the 2 in there. So it's something to keep in mind that this is not in a 1-to-1 scenario, so you do have to do those extra steps. So that is what I'm going to go ahead and end on, so that I have time to get ready for my meeting at 9 o'clock. Hope this has been helpful. We still have office hours this week to help you guys out, and good luck on your exam on Saturday.